Good morning. Let's see how this goes. Just as a heads up, my dog has a vet appointment that's been scheduled forever when I didn't know I was teaching you guys. So it's on Wednesday, and she's fine. She's just blind, so she's going to an ophthalmologist. But so on Wednesday, I'll just post a video for you guys to watch from when I taught it with my guys. And so let's see if I can use this surface. Wish me luck. And of course, I'll figure out how to post these notes after class like I usually do. So for class on Wednesday, I will post, looks like I write really big, I do, but I will post a video because I can't be available during class time. What's nice, I guess, if you want to look on the bright side of things, is that you guys have your test. You have a test on Friday, right? So Shaun's going to invigilate that, and so you've got a test on Friday. So what's kind of nice is if we don't have a sit down class like this on Wednesday, then you can use that time to study, and then maybe get caught up on Wednesday's class at a later date. So I don't know, might be nice, because this week's stuff is not on the test. So the topics from this week will not be on the test. Right. And let's see, now I'm just playing around here. What I mean is we're starting chapter 4, right? So chapter 4 is not on the test. It's going to go up to 3.1, which is what we did last day. All right, so because we had a nice clean break, and we basically spent all of Friday just going through 2 very large examples of using quadratics to solve kind of problem solving. So I'm going to leave that, and you can review it on your own time. Hopefully you found the videos that I post from, I realized I didn't have a link, or I could have sworn I posted a link, but there's a link to the YouTube videos on your Moodle now. So in case it wasn't there before, I really thought I had, but anyways, no matter. So chapter 4 is on exponential and logarithmic functions. Exponential and logarithmic. I should write it properly. I'll try to write it properly next time, because I'm not very good at erasing on this thing yet. Exponential and logarithmic functions. Okay. So we'll start with exponential functions in 4.1. So exponential functions. Exponential functions are things that look like f of x equals a to the x, right? Where we notice that the variable x, right? Let's see if I can, oh, maybe I can, there. The variable x here, they're in the power, right? So the variable the variable x is in the power, which is what makes it an exponential function. An exponential function base A, right? So whatever we have, is there some sort of pointer on here? Maybe. Nope. Sorry, just getting sorted out on this here. So far, so good. Hey, Jared. Yeah. Is there a pointer on this thing?
No, I don't think so.
No?
No.
Okay, that's okay.
Sorry.
That's okay. What a messy day. Okay, so anyways, there's no pointer. So here I will just use a different color. That's our base A. Just a second. I don't know how to. Just strategizing on how to get you guys through this class. Okay, so we have this base A, right? And we're going to refer to the base quite a bit. So we need to know what it is, but it's pretty self-explanatory, right? It's the base of our exponential function. And just remember that an exponential function has the x, the variable, in the power, right? Versus a power function. So versus a power function, which would be something like f of x is x to the a, right? Where x is in the base. Okay, so we've already dealt with power functions, so now we're dealing with exponential functions. But it's good to kind of keep track of what's going on. Notice that when the x is in the power, right, if we have to solve for x, we need to develop some sort of method to bring that x down. And we're not going to get there until section 4.3, but hopefully that's a little bit later today. So that's kind of where we're headed, to be able to solve these problems with x in the power. But in 4.1 and 4.2, we talk about just exponential functions. What do they look like? And we'll just kind of go from there. Okay, so here I'm going to add that a is going to be greater than 0 and a is not equal to 1. Okay, a can be less than 0. Oops, hey. Greater than 0, and this does not look like. Okay, so the thing here, let's see what this does. Oh, so maybe that is a pointer. I think it's more of a cut and paste thing, but that's okay. A can be less than 0, right? But what happens if you think about a here, right? Oops, I don't know if what I was doing was very clever. So in a to the x, if you have a being -2 and x is 2, right? Then you have -2 to the power of 2. Anything to an even power becomes positive, right? And so we always get these positive values. Whereas if we have -2 to the power of 3, right? That's -2 times -2, which puts me at 4, times -2 puts me at -8, right? And so now I have a negative number. So the reason we have a greater than 0 is not because it can't be less than 0, it can, but because it flip-flops back and forth between being positive and negative. So we're just restricting that and saying, okay, a is going to be greater than 0 for what we're talking about. And the a not equal to 1 is only because it's not interesting, right? 1 times 1 times 1 times 1 times 1, it's just going to give us 1, who cares, right? And so we're putting those restrictions on only because it makes it kind of more interesting. So, oh, what? Still on green, huh? On your calculator, whatever you're using as your calculator, evaluate the following. Just so we can make sure that you know how to do these on your calculator, and it seems silly, but we're going to make sure that we're all on the same page. So 2 to the power of 3, okay, I don't know if you can see, I can't see really what I'm pointing at here, but I have this x to the power of blank button, and on here I don't have Desmos, so I can't show you on Desmos, but you should be able to find however you want to do your powers on whatever calculator you're using. So 2 to the power of 3 is 8. Okay. 2 to the power of pi, now you should be able to find a pi button on your calculator because pi is a constant, so you want to use the whole thing. 2 to the power of pi is roughly equal to 8.824977827. And let's try 3 to the power of 5. 3 to the power of 5, just make sure you've got it, is equal to 243. Okay. So the graph of an exponential function is going to vary depending on if the base is greater than 1 or less than 1. So notice that here we have this kind of a greater than 0 and a can't be 1. So there's a little gap there between 0 and 1, and then 1 and up, right? And so what happens is that the graph of an exponential function depends on whether a is between 0 and 1 or if a is greater than 1. Okay. So what happens is, notice that, I moved my desktop down and now I keep kicking it, and that's not very good, is it? So here, what we have, if a is between 0 and 1, then we have exponential decay. Oh, maybe I'll fix that. Exponential decay. Okay. Whereas here, if a is greater than 1, so if the base is greater than 1, then we have exponential growth. Okay. So what that looks like in a graph, let's see if we can kind of sketch something out here. Okay. Let's do the exponential decay first in blue. And so exponential decay is going to look something like this. Okay. Exponential growth we'll do in green. Now, one thing that's really kind of interesting, but if you think about it, it makes sense, is that they'll go through the same point here, which is at 0, 1. If you think about any base, right, if x is 0, so if you have a to the power of x, if we let x be 0, then a to the power of 0 is 1, right? So anything to the power of 0 is 1. And so any one of these exponential functions will always pass through 0, 1. So what this looks like, the growth function is going to look something like this, right? And so here, since anything to the power of 0 is 1, all exponential functions pass through 0, 1. Okay, so for the growth and for the decay, what happens is we have this. Now let's see if I can maybe pick something here, right? We've got these asymptotes at y equals 0. Okay, I don't know, that wasn't very helpful. Okay, but notice that both exponential functions have horizontal asymptotes at y equals 0. Have horizontal asymptotes, which just means that they're going to approach the x-axis, right? So y equals 0 is the x-axis, but they're never going to get to the x-axis, right? So they're never going to cross over. They're just going to approach the x-axis and then just kind of go till infinity. So notice that both exponential functions have horizontal asymptotes at y equals 0. Okay. If a is greater than 0, or sorry, greater than 1, oops, it's always greater than 0 for what we're talking about, then y is going to go to infinity, right, as x goes towards infinity. Okay, so if we look at this here, so if a is greater than 0, that's the green one, so let's see here. Right, so as x goes to infinity, right, y goes to infinity as well. So as x goes to infinity, y goes to infinity. Okay. And then, of course, the other direction, as x goes to negative infinity, right? So if it's going in the left direction, then y is going to 0. Okay. I'll add that down here. So if a is greater than 1, then y goes to infinity as x goes to infinity, and y goes to 0. Goes to 0 as x goes to negative infinity. Right, so we're going to talk about the relationship as x goes to positive infinity or negative infinity. Whereas if a is between 0 and 1, then as x goes to positive infinity, now let's look at the graph here. So as x goes to positive infinity, that's out this way, right? Then y is going towards 0, right? It's approaching 0 as you go down. And same thing up here, as x is going to negative infinity, right? What happens to our y? It looks like our y is going to positive infinity. Okay, so then as x goes to infinity, what happened here? I don't know. Something happened on my screen. So then as x goes to infinity, y goes to 0. And as x goes to negative infinity, y goes to positive infinity. Yeah. Okay. So, what will, oh, hey, what happened here? Uh-oh. Now I've done it, huh? You zoomed out. I should have just left it. Okay. So what happens is, okay, our different bases, well, what happens as we increase our base gets steeper and steeper. So it kind of dictates how steep our graph is. Let's see here. Maybe I'll just skip that part because usually I just bring in a little graphic, but I guess I can do it. Where is it? Where is it? Where is it? No. Okay. So if we've got a graph like this, we can have a look at a few different graphs. Okay. If we are talking about exponential growth functions, the hardest part here is going to be for me to try to go through the origin at the same point for all of these. So if we let this be y equals 10 to the power of x, and then, oh, you know what? I need to make it like more steep, like this. Y equals 10 to the power of x. If we do 5 to the power of x, y equals 5 to the power of x. Y equals 2 to the power of x, let's say. Okay. Same thing. So the steepest version is going to be with the smallest base for the decay. So y equals 1 over 10 to the x. Notice that 1 over 10, right, is between 0 and 1. And so now we have this decay function. I'll do arrows both ways, I guess. And we can have something like y equals 1 over 5 to the x. And then 1 over 2 is going to be even less steep. Hard to see. Usually I have a nice graphic that I just pull in. But so notice the graph becomes steeper for growth models as the base increases. And notice, right, that the graph becomes steeper for decay models as the base becomes smaller. Okay. So notice the graph becomes steeper for decay models as the base decreases. Right. 1/10 as the base is the steepest, and then 1/2, which is larger than 1/10, is kind of less steep. Okay. There we go. So what we can do is, if we know one point on an exponential function, we're able to find the equation of that exponential function. So given a point on an exponential function, we are able to find the equation. Okay. So, because what we have, a point, right, is really an xy coordinate, which means that at one point on the graph, we have the x that corresponds to that y. And so we use that, and that happens a lot in math, right? We have a point, and we need to think about that point as xy, and so that means we have an xy coordinate. And so oops. Hey, where does it keep? Find the equation of the exponential function. Oh, your screen sharing is okay. Hopefully that's okay. I don't know, I keep hitting stuff. Find the equation of the exponential function through the point. Let's start with 327. Okay. Remembering, right? So we have f of x is a to the power of x. Okay. So here, let's switch over here. This is x, y, right? And remember that f of x is really y, right? It's the output, which is our y value. And so really what we have is we have y equals a to the x. Well, I know that when x is 3, y is 27. So what if I use that to find a? So I have 27 as my y, and oops, not 3. A to the power of 3. And now solve for a. Okay. So if I have to solve for a, I can take the third root of both sides. Third root of 27 is a. And if I do 27 to the power of 1/3, that's the third root. So I get 3 is a. So therefore, f of x is a to the power of x, where a is 3. So we have f of x is 3 to the power of x. Okay. And then because 3 is greater than 1, we have a growth function. So it's going to look like this. All right. Okay. How about we do another example? We'll give you guys just a little bit of time. So again, find the equation of the exponential function. Find the equation of the exponential function that passes through the point through the point 4 and 1/16. Sketch the graph. Okay. So I'm just going to pause this here, give you guys. So let's start working through this. Let's note first that x would be 4 and y would be 1/16. Okay. So if I start with my f of x is a to the power of x, and I let f of x be 1/16 is a to the power of 4, okay, then I'm going to take the 4th root. Okay. So I'm going to take the 4th root of 1/16 is equal to a. So what I'm going to do, I could use the exponent laws, right? The 4th root is to the power of 1/4, which I could bring in 1 to the power of 1/4 is just 1. And then 16 to the power of 1/4 is the 4th root of 16, right? Or I'm just going to use my calculator. So I'm going to have 1/16, put that in brackets, to the power of, and then again in brackets 1/4. I get 1/2. So 1/2 equals a. So therefore, we have something like f of x is a to the x, but in this case, f of x is 1/2 to the power of x. Noticing, right, that this is between, so a is less than 1, it's greater than 0, right? So it's a decay function. And I can graph this, right? It's going to look something like this. Weep. Okay. What's true for all of these, right, is that they'll always pass through 0, 1. Okay. And what we were given was that it passed through 4 and 1/16. So if I have 1, 2, 3, 4, this point here is at 4 and 1/16. Okay. Which makes sense because it's really, really close to 0. It's not 0, but it's close to 0 because it's already approached that, that x-axis. Okay. Just like other functions, we can graph these, we can manipulate these graphs, we can build more complicated graphs from the basics, right? So just knowing that if it's decay, then it's going down like what we had here, right? And if it's growth, then it's going up like this, right? I've got to delete those, but just wanted to show you. So we can use transformations to manipulate the graphs, of an exponential function, which means we have to remember all those manipulations, right? From section, we'll say 2 point, let me see here. Where did I have it? 2.6. Use the methods developed in section 2.6. Okay. So things like, okay, if I add something to the y, that means I move up my whole graph on the y-axis. If I subtract from the y, then I'm moving it down. If I add to the x, I actually shift it to the left by that much. If I subtract from the x, I move it to the right, which to me is a little bit backwards, but that's okay. If I negate the y, then I flip on the x-axis, right? Because anything positive becomes negative. If I flip on the x-axis, then I've negated my x values, right? Because they went from positive to negative. What else did we talk about? Oh, stretching and shrinking. So depending on if you're manipulating your x or your y values, right? The y values behave like you think they will. So if it gets bigger, it expands, or if it's smaller, then it contracts. So just flip back to that section, and then you'll have that kind of at the ready. But let's do an example. Draw the graph. Draw the graph of, f of x equals 3 minus 2 to the x. Okay, keeps there. And find the domain, range, and horizontal asymptote. Oh, that doesn't look like H, does it? Horizontal asymptote. Okay. So, just as a refresher, right, you start from your core function. So here, this would be your core function. That's going to be useful, right? Because if you know what 2 to the power of x looks like, then you can follow a couple of points around, right? So if you figure out what 2 to the x in general looks like, you can pick 3 points. 0, 1 is always on there, right? So you can always follow the y-intercept. And then, so from the core function, we know our original graph looks like this. Our original graph is something that looks like this. So 2 to the power of x, I know I have this growth function. Whee! I know it passes through, so 2 to the power of x, I know it passes through 0, 1, but let's also figure out maybe 2 more points that we can follow around. So here, when x is 2, 2 to the power of 2 is 4. And when x is maybe negative 1 might be nice. Oops. Negative 1. When x is negative 1, then I'm at 1/2, right? 2 to the negative 1 is 1 over 2. But just make sure 2 to the negative 1 is 1/2. Okay. So what we can do is we can follow these 3 points around. Okay, and just to kind of confirm. We can follow some points around until we get to our final graph. Until we get to our final graph. Okay, so let's talk about how we build this out. So we start at our core function, right? And then to our core function, we negate it, and then we add 3. Okay, so we're gonna work through these. So now find the graph. Now find the graph of f of x equals negative 2 to the x, right? The negative in front says to flip, right, on the x-axis. So reflect on the x-axis. Okay. All it's saying is that make all your y values negative, right? So all your x values stay the same and your y values become negative. So from here, 0, 1 becomes 0, negative 1. Negative 1, 1/2 if the y becomes negative. So make all y values negative is what it means. So negative 1, 1/2 becomes negative 1 and negative 1/2. And 2, 4 becomes 2, negative 4. Yeah. So let's see here. Okay. I also know from up here, right, that I never approach, or I never cross the x-axis. So now when I flip this over, I'm going to have this same behavior, right, this asymptotic behavior going here. Okay, maybe I should use a different color. I'm going to move this point here. Hey, look at me go. Let's say this is at 2, negative 4. Okay. So now we've got this kind of flip. So we flipped it on the x-axis. Okay, but notice how it's, well, it doesn't look that great, but that's just my drawing, right? So I'm not very good at drawing, but it helps to have these kind of points that we can follow around, right? And then, so now from our core function, right, now we're here at negative 2 to the x. All we have to do is we have to add 3 to each of these y values. Okay. Now we can find the graph of f of x equals 3 minus 2 to the x, where, so this is where we were, and then we have to add 3 to each y value, right? We move the graph up by 3 points. Move the graph up 3 points. Okay. So each of these y values is going to be, I'm going to increase them by 3 points. Okay. So now, from 0, negative 1, I'll start with that one because it's the easiest. So from negative 1 plus 3, that puts me at 0, 2. Okay. From -1 and -1/2, -1/2 plus 3 puts me at 2.5. So -1 and 2.5. Okay. And let's see here. 2, -4, if I add 3, right? Then I'm going to, what am I going to have here? So if I, -4 plus 3 puts me at -1. 2, -1. Okay. Keeping in mind too, right? So here we have this, this asymptote here, this horizontal asymptote at y equals 0. That's also moved up 3 points. So now here at y equals 3, we have this horizontal asymptote. Right. Of course, my graph doesn't look very good, but it's the best I've got. So my final graph then might look something like this. Okay. So I reflected and then I moved it up, and now we can answer the rest of the problem. So this is my final graph, and I can find things like the domain, the range, and also the horizontal asymptote, right? So the domain here, there are no restrictions on the x values that I can put in. And that's in general for exponential functions, so that's really nice. So the domain is the set of real numbers. Oops, I should make that nicer. Okay. So the domain is the set of real numbers, which is going to be true for any exponential function. The range, it seems to go up to, but not including 3 and down, right? And so what we write is we can write y is less than 3, right? Never equals 3. Never equal to 3. That's important, right? Because it's a horizontal asymptote, so we're never going to get to 3, but it's going to approach 3 and get very, 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 very close to 3. And finally, the horizontal asymptote we already saw it, right, is at y equals 3. Okay. Okay, so let's do just a quick example. I'm not actually going to do it. I'm just going to talk you through the steps. Okay. So how would we graph something like f of x equals 1/3 all to the power of -x minus 2? Okay. This one's a little bit tricky because what you have to do, right, you have this exponential function, okay, which is basically the core function, right? But then over here, right, -x minus 2, you might be tempted to, okay, I have to flip on the y-axis because my x becomes negative. So from positive, I become negative. Okay, that's a flip on the x-axis. And then moving over to the right by 2 units. But we have to be careful because we can actually pull this common x outside, right? And so what's going to happen, clean this up a little bit. We pull out the common negative, before transforming. Okay, so what we get is we get f of x is 1 over 3, right? So a base of 1 over 3, I already know that if my base is 1 over 3, then I have this decay function, right? So maybe I can write that here, right? I've got a decay function and negative x plus 2. Okay, so what I'm going to do is, it doesn't actually matter the order that you do them, right? You can either shift it to the left by 2, which is x plus 2, and then flip on the x-axis. Well, maybe it does. So here, shift graph to the left by 2, and then here, reflect on the x-axis. I said it didn't matter, but it does. Why would I say that? So, but because you've got the x plus 2 in brackets and then it's negative, right? You're going to deal with this one first, right? This one here, and then you're going to reflect it around the x-axis. Okay. Always check your work in Desmos, right? So just make sure that when you plug in this original function here, you end up where you should, right? So this one here is what you should be looking at the end, right? If that's not the case, then something went wrong. I wish I had Desmos on here, but not today. So that's okay, but just try it in Desmos, graph it out, make sure that you get the same graph that you think you should have. Right? Okay, so consider a power function f of x equals x to the a, right? And an exponential function has the x in the power, a to the power of x, which grows faster. Okay. What we can do, right, is if we just let a be 2, for example, right, then we can consider a bunch of different x's, right? So x to the power of a is x squared, and then a to the power of x is 2 to the power of x. So if we let x be 1, then 1 squared is 1, and 2 to the power of 1 is 2. So already the exponential function is kind of in the lead here, right? Exponential, and here's the power. If I let x be 2, then I have 2 to the power of 2, which is 4, and 2 to the power of 2, which is also 4. They're the same. If I let x be 3, I've got 3 to the power of 2, which is 9, and 2 to the power of 3, which is 8. Okay, So kind of started out in the lead, and then now it's lagging behind. So let's skip 4. Actually, may as well do it, easy enough. 4 to the power of 2, 16. 2 to the power of 4 is also 16. How about 5? 5 to the power of 2 is 25, and 2 to the power of 5 is 32. We go to 10. All of a sudden, I'm at, so 2 to the power of x. X is, so 10 to the power of 2 is 100. And 2 to the power of 10 is 1024. I don't know why that took so long. But let's do 100 to finalize this, right? But already here, this is way, way larger than 100, right? 1024 is much larger than 100. But let's just do x equals 100 to make sure. So I've got 100 to the power of 2 is 10,000, so quite a bit. And 2 to the power of 100, is huge. 1.2676506 times 10 to the power of 30. That's really large, right? So what we see here is that exponential functions grow faster, right, than power functions. Grow faster than power functions. Nice. So there are some fun things that we'll kind of skip in this section, but kind of a real world application of exponential functions is compound interest. So just kind of an economic perspective. Sounds like a textbook. An economic perspective. But we're going to leave that for now. So 4.2, we're just going to talk about the special case of the natural exponential function. So the natural exponential function is f of x equals e to the x. Oops, that looks like a c. It's e to the power of x. Okay, so this is the special case because e is approximately, and you should have an e button on your calculator. Sometimes if you're working in the Desmos calculator, for example, you might have to use exp and then in brackets what the power is. But e to the power of 1 is just e, right? So if I have e is roughly 2.7188281828. There's a song, it's just like pi, it keeps going forever and ever and ever. And so it's roughly 2.72, but you have to use the actual button, right? So we want to use e, which is the exact value. So it's this constant, irrational constant. Okay. E to the x is the only exponential function which has a slope of 1 at the y-intercept. Now, that's not going to be interesting until calculus, right? But it will be very interesting once we get to calculus, right? So presumably you're going to keep going and take calculus after this. So e to the power of x is the only exponential function whose slope is exactly 1 at the y-intercept. At the y-intercept, which is at 0, 1, right? For all these functions, e to the power of 0 is still going to be 1. Anything to the power of 0 is 1. But what's interesting is that it has a slope of 1, and that makes it really useful later on. Okay. So e to the power of x is going to look something like this. E, 2.7, right? This greater than 1. So we've got this growth function going through 0, 1. Okay, and what we're saying here is that at this very point, the slope is 1, right? If we just touch at 0, 1, the slope of this thing is 1. Okay, so on your calculator, just to make sure that you have this E button figured out, on your calculator, find e to the power of 6. Oops. Okay, so just make sure that you know how to do e to the power of 6 on your calculator, for example, right? E to the power of anything. You should have roughly 403.4287935. Okay. So make sure you get roughly that. Okay. So before we end today, I just want to introduce logarithmic functions just so we have it kind of under our belt a little bit. And then, like I said, I'll post a video for class on Wednesday because I won't be able to be here. And I haven't heard from Shaun, but I don't think he's quite well yet. So let's see here. So 4.3 is on logarithmic functions. So if we talk about exponential functions, and here we've got an exponential function, right, that we just talked about. Any exponential function passes the horizontal line test, right? I can draw horizontal lines at any point, right? And I only cross the graph once, which means that it's 1-to-1, right? The horizontal line test tells us that it's 1-to-1. Which also means if it's 1-to-1, it means that it has an inverse. And that inverse is the logarithmic function. Okay. So notice that all exponential functions pass the horizontal line test. Pass the horizontal line test. So they have an inverse. Yeah. The inverse of an exponential function, the inverse of an exponential function is the logarithmic function. Now I'll try to write it properly here. Is the logarithmic function. I always have to spell it out. Okay, so if f of x is a to the power of x with a greater than 0 and a not equal to 1, oops, I should say and, oops, and a not equal to 1, okay, then the inverse of f of x, oops, it's the eraser here, then the inverse of f of x is going to be the log base a of x. So what we would say, you would read this as the log base A of x is how you would read this. Okay. So that tells me that if, or in other words, if I establish that the log base A of x is y, that means the same thing as a to the power of y equals x. Okay, so notice how we're going from, so a to the power of y equals x. Okay. A to the power of y equals x. So it is really weird to look at this and go, oh, okay, well, these two things are equivalent, right? So whether I want to rewrite this as a logarithm, I can. Log base A of x equals y, right? I can kind of bounce around, but to establish this relationship is really important. And it is kind of really confusing, especially in the beginning. Okay, so this base A is the same in both of these, right? So A, and then x is equal to x and y is equal to y. Find, or sorry, I should say evaluate, not just find, evaluate log base 2 of 8. Okay. What we want to do is, without using your calculator, and I want you to see if your calculator has a fancy log empty base button. So here, this calculator, for example, I don't know if you can see, has a log with an empty base, which means I can put in any base. You don't have to. Most calculators only have an LOG button and an LN button, which we'll get to. But the log button is the log base 10, so that's not going to quite work here. But what we have to do is we have to say, okay, 2 to the power of what equals 8, right? So here, so 2 to the power of y equals 8. Okay. So we need to figure out what y is here, right? So 2 to the power of, well, 2 is 4. 2 to the power of 3 is 2 times 2 times 2, which is 8. So by trial and error, oops, by trial and error, or just kind of knowing some of these basic powers, by trial and error, we know y is equal to 3. So therefore, the log base 2 of 8 must be 3. Okay. Which I can check on my fancy calculator. Log base 2 of 8 is 3. Nice. What if we have to find, so now do the same thing, evaluate the log base 10 of 1 over 100 equals y. Okay. So we have to do that same thing, right? We have to take 10 to the power of y equals 1 over 10, or sorry, 1 over 100. So 10 to the power of y is 1 over 100. Notice that 100 is just 10 to the power of 2. right? And so we notice, we see, so again, 100 is really just 10 to the power of 2. So it really helps to know some of these common powers, right? You can trial and error it, right? It has to relate to 10 somehow. So 10 to the power of 2. And so 1 over 10 to the power of 2 is really 10 to the negative 2, right? That's how we brought it downstairs, is negating that power. That's from way back in chapter 1, but really useful now, right? And so what we find is that, so therefore 10 to the y is really 10 to the negative 2. So y must be negative 2. Which I can try on my fancy calculator, and because it's log base 10, and I already jumped ahead a little bit here, and told you that the log button on your calculator, the default log button is log base 10. So you can do log base 10 of 1 over 100, and you should get negative 2. Good. Okay, so before we end here, let's just talk about some properties of logs, just so we have them under control. Log base a of 1 is always going to be 0 regardless of the base, because, right, a to the power of 0, anything to the power of 0 equals 1. Anything to the power of 0, we've already talked about that today, right? A to the 0 is 1, fine. How about the next property of the logs, log base a of a? Well, that must be 1, right? Because a to the power of 1, a to the power of 1 is a, right? How about log base a of a to the x must be x, right? A to the power of x is equal to a to the x, right? Fair enough. So how we're going to use this, though, is if we have the same base here and here, then we can eliminate the log and the base a, and it just drops down to the x, right? So that's how we're going to be using it later on. We can take the log of the same base to, or as a to the x to isolate x. That'll make more sense later. Same idea, I know I'm out of time here. A to the power of log base a of x, or just about, is also x, okay? Because you have a to the power, now let me see here. A to the y, right? Since a to the y equals x, right? Let y be the log base a of x. Okay? So what you're doing is you're just taking this in here, and then it drops out and you just get x. Right? So again, we use these two properties to solve for x. We use these properties to solve for x. Okay. And that's the end for today. But I'll just make a note here Next class will be a pre-recorded video hosted on Moodle. Something tells me that I'll be seeing you again because I think Shaun's voice is just not cooperating this term. So I hope to see you again. If I don't get to see you, it's been a pleasure. And good luck on your test on Friday.
All right. Hopefully see you around.
Thanks.